Hi, I'm Arthur Wang. This is my Lab 5 Choose Your Own Adventure lab report. So the experiment will observe the motion of a falling slinky. We'll then construct an observed position versus time graph through the use of Tracker to analyze the video. Next, we'll construct a computational model in GlowScript to model theoretical movement of a slinky. And finally, we'll analyze the motion of the slinky in question. So the subject. So my experiment examines the position versus time function of a slinky in the following Veritasium video, as in it will examine the bottom of the slinky. So these are some key concepts that will be relevant. So we have Newton's second law and turbulent drag force, or just a drag force. So we have the velocity update formula, V final equals V initial plus F net divided by mass times delta t. Then we also have the position update formula, R final equals R initial plus V average times delta t. These are both derived from Newton's second law. And then the last formula we have here, this is the drag force. So we have the drag force equals negative b times v squared times v hat, where negative b is the drag constant. So modeling slinky motion with drag force. So my computational model code for gravity with drag force applies Newton's second law in updating the position and the velocity. So code implementations of the formulas for velocity update and position update on the previous slide. So they're right here, ball dot velocity, and this is the velocity update, and this is the position update. And then also we have an implementation within the code for the tension force that will be that the force will have that the spring will have exerted. Otherwise, without implementing the tension force, the spring, or at least this model, will cause the spring to look like it's falling far too fast, because the tension force causes there to be an upwards pulling motion. So the time interval was chosen based on the tracker data for consistency. So we have this time interval and then this time interval, and these are where the top of the spring catches up to the bottom, and this is where it is already caught up and both of them start to fall. And this is where like the implementation of the drag force is active. And then we also have the initial position, and then we also have the initial velocity, as well as the unit vector, which points straight up. And so we also implemented, yes, the drag force equals negative b v squared times v hat in code format, which is again down here. So next, data and analysis. So here's the GlowScript, and here's a pretty admittedly low-res version of Tracker. So we have the bottom of the slinky is modeled with the axis being aligned with the top of the slinky being at y equals 0, and the graph shows that the bottom stays stationary until the top of the slinky reaches the bottom, where it then falls. So it's at this point where it then falls. Otherwise, it's staying flat until it finally decides to decrease. There is a tension force within the slinky that balances out gravity by pulling upwards until the slinky was fully compressed, which is at this point again. And the tracker data shows a similar trend in which the slinky's bottom stays still until the top catches up. So it also does the same thing where until it reaches a specific point, it stays flat until it goes down. Okay, so conclusions and ideas. Due to the properties of a slinky with a tension force as well as a drag force, the bottom of the slinky remains stagnant at a fixed position in the air as long as the slinky's top has not caught up, aka when the slinky is fully compressed. Only when the slinky has achieved full compression does the bottom of the slinky fall to the ground, with the top falling right behind in a compressed coil. It would be slightly interesting to plot the movement of the top of the slinky as well, in relation to the bottom of the slinky to see the catalyst point that causes the bottom to stop floating in midair. Thank you for watching my lab report.